Hi everybody, Dr. L here, and we're going to pick up our discussion of logistic regression, specifically for classification. And in this segment, we're going to follow up on the last segment in which we had kind of taken a look at using the linear regression model for a classification problem, specifically a binary classification problem where your y variable is either 0 or 1, belongs to one class or it doesn't. This is the type of environment that we are looking at applying the logistical regression to. So that being said, we can use linear regression for dealing with this task. In fact, we're going to wind up concluding this particular segment looking at something called the linear probability model, which again is a situation where you can implement just a basic linear regression when you have y data that is binary, 0 or 1. The logistic regression model is really going to provide us a better solution to that particular framework where we have some y variable that has 0 or 1 outcomes, whereby we are able to estimate a probability somewhere in between 0 and 1. That was the benefit of logistic regression, is that it actually gave us a continuous output between 0 and 1 that we could interpret as a probability. So we dealt with both of these in the last segment. In this segment, we're going to talk a little bit about how to apply gradient descent. It's a little bit more theory, specifically in the context of logistic regression. So that way, when you're running it, whatever software package you're running it, if it's R, when you see them reporting Fisher scoring iterations, for example, you'll kind of have an idea of what's going on under the hood and how the search for the optimal parameter works. So we're going to talk about that in this particular segment. And we're also going to follow up on a comparison again to the linear regression model at the very end, something known as the LPM, or the linear probability model. And this is again another option here for implementing linear regression, that one-step learning estimation technique in the context of a binary classification problem, but it has some serious drawbacks. So you should not be, I think, really thinking about applying linear regression in any form. Whether it's the threshold S form versus the LPM, they're both, I think, inferior to the logistical regression for trying to achieve this task that is binary classification. Now, we concluded the last segment by looking at rewriting this logistic regression equation. So this was why we call this thing a nonlinear regression equation, is because the beta parameters show up as really an exponent on this natural number e, right, 2.7 something. And they show up in the denominator. So the betas show up non-linearly here. And what we saw in the last segment is we can actually rewrite the above equation in a slightly different form, where we can write it in terms of something known as the odds ratio. And in fact, if we took the log of both sides, we would actually have the signal on the right-hand side. All those e's would go away. We would have beta 0 plus beta 1x1 plus beta 2x2. And after rewriting the regression equation in this form, we can really think about the multiplicative value, e to the beta. Okay, this can be interpreted as really 1 plus the odds ratio resulting from a 1 unit increase in the input x, holding all other factors fixed. So if you estimate your betas, right, R or whatever your software packages, report your betas for the logistic regression estimates, and you take that beta and you raise it to the base E, right? So you have E to that beta value that you estimated. That will give you some number, some positive number, but it's going to give you some positive number. And if it's bigger than 1, okay, that will happen when the beta value is bigger than 1. So you're still getting the result that if the beta is positive, then that variable has a positive effect on the likelihood of y happening in the logistic regression framework. And if beta is negative, then e to that beta will be smaller than 1. So when you multiply the other e to the beta terms by e to the beta for the variable you're looking at, it has the effect of shrinking the entire left-hand side of the expression, which is the odds ratio, meaning if the left-hand side gets smaller, the likelihood of the event happening is getting lower. If e to the beta I equals 1, that means the beta value itself is 0, right? Anything to the 0 power equals 1, and that tells you that the x variable itself has no significant effect on the likelihood ratio. So we're going to talk a little bit about constructing the error function, right? The cost function, in order for us to implement a machine learning technique, specifically gradient descent, to calibrate the logistic regression or to estimate those optimal parameter values. And the way we do this is really predicated on a technique known as the maximum likelihood technique. And what we're essentially going to do is we're going to write out a function that describes the likelihood that we would observe our data given the model that we are proposing. And what we're going to do is we're going to calibrate the betas by making it as likely as possible that we would actually observe the sample of data that we have. Okay, so that is the idea behind maximum likelihood. Now you might be wondering, well, I thought we solved cost minimization, not likelihood maximization. We're going to write out the problem in terms of likelihood maximization, and then we're going to use a little trick. We're going to make the objective function negative. So instead of maximizing the likelihood, which is what we want to do, we're going to minimize the negative likelihood function. And we're going to make the negative of that likelihood as small as possible, which gives us the solution to the maximum likelihood problem. Now, the likelihood function is kind of an ugly thing to construct here. So I'm going to go through some of the basics rather quickly. But for every pair of observations, X and Y, X the input data and Y the Y outputs, right? Y is generated by some data generating process. And that process, what is that doing? Well, it is a function that associates the probability of Y with a particular value of the X's. And the question in thinking about measuring the likelihood of observing the sample is essentially the following. If our optimal hypothesis turned out to be the same as the data generating process, if we made the right guess, okay, what is the probability we would actually observe our sample? Meaning, what is the probability we would be likely to get our Y values from the X data that we actually have here? Okay, and what we're going to do is we're going to estimate this probability. What is the probability of observing a particular sample, right? So what we're going to calculate here, we're going to think about, first off, the conditional probability of Y given X. Okay, that is what we are actually estimating. That is what our hypothesis is in the logistic regression framework, right? We're trying to estimate the probability that Y is going to occur given the particular X features that we are conditioning on. And the form of the hypothesis, H of X, right? We want that hypothesis to classify Y correctly, and that is the probability that Y belongs to the class, and 1 minus H of X then is the probability that Y does not belong to that class. So in this slide here, it looks like we've coded it belonging or not belonging by plus or minus 1 here, but you could easily call that 0 or 1 if you wanted to recode it, or 1 or 2, or however you wanted to recode it. Now, the likelihood function itself, what we do here is we want to compute the probability of observing Y given X in our data. And given the logistic regression function, we know what that looks like. That is the theta of, right? Theta is that transformation function, that logistic transformation function. It's the logistic transformation of the signal. And what is the signal? Well, the signal is beta 0 plus beta 1 x1 plus beta 2 x2, so on and so forth. And that is right here. That is our signal. Okay. So we want to calculate the likelihood here of observing every set of observations, right? These are all different observations, and we want to calculate the likelihood of observing all the observations in our training data. And the way we're going to do that is we're going to calculate the likelihood of every single observation occurring in the form it has. Okay, and you remember, if the observations we're assuming here are sampled independently of one another, then the way we can calculate the likelihood of observing each observation, the first one and the second one and the third one, okay, is, you might remember, we have to use the multiplication rule, right? I want to observe the probability of having the first observation and the second and the third, all the way through observation n. So the way we were going to calculate this likelihood of observing all of the data points jointly is by taking the product of all of these probabilities. This is so this Greek letter pi here, that stands for we're going to multiply all of these probabilities. Okay, we're going to multiply all these probabilities from n equals 1 all the way to capital N, the number of observations in the training data. And that is equivalent on the right-hand side of the equal sign to just multiplying the logistic regression probabilities, okay, for all the cases where we had ones and zeros in our data, and multiplying those probabilities up. So that's what we want to do. We want to try to compute the likelihood, okay, of observing the sample, and we're going to use this as our objective function to calibrate the beta parameters to maximize this particular likelihood. Now, before we do that, what we're going to do is we're going to transform this likelihood function. So again, this whole kind of ugly term we're looking at here, this is the likelihood function. And we're going to transform this thing, which looks like a bunch of things multiplied together. You know, the theta for every observation multiplied together. That is what this likelihood function looks like. And what we're going to do is we're going to transform it from a multiplicative function to an additive function. And the way we're going to do that is by taking the natural log of a function. So you might want to recall here at this point, an important property of the natural log function is if you have the log of the product of two numbers, x times y, okay, this simplifies to the log of x plus the log of y. And right now, in this green circle here, okay, we have a bunch of things multiplied together, a bunch of these theta of terms, okay, for every observation in our training data. And they're all multiplied, and we want to change them from them being multiplied to them being added together. So we get some sort of linear result. And we're going to do that by taking the log of what is circled in green here. And once you do that, we would be computing what is called the log of the likelihood function. And what we're going to do is we are going to negate that. Okay, we're going to put a negative sign in front of it. And once we do that, we're going to be able to change the maximization problem to a minimization problem. We're going to minimize the log likelihood function, technically the negative of the log likelihood function. So let's go ahead and look at that. We're going to negate the likelihood to transform the problem into a minimization problem after we take these natural logs. Okay, and once we do that, we're going to wind up in the following situation. So what we've done here, okay, is we pulled that 1 over n out front. So we're kind of measuring an average of something. I'll show you that in just a moment. Okay, so that 1 over n wasn't really there in the previous slide. And we're going to take the log of the product of things. So what are we doing there? Well, this is the likelihood function that we had in the previous slide. We're going to take the log of it, which means in the next line, that pi symbol, which was representing us multiplying a bunch of stuff, winds up changing to a log symbol. Or sorry, not a log symbol, but a sigma symbol, which represents us adding up a bunch of things. So now we're adding up all these log terms. And if you're wondering where did that negative sign go out front, well, we brought it in front of the log, and there's an important log property. If you have any number in front of a log, you can actually bring it inside and make it the power of the number inside of the log. So what we had here was we had like -1 times the log of something. And what this is actually equal to is the log of that something raised to the -1 power. And hopefully remember, anything to the -1 power is just that something right underneath 1. So that is where this fraction came from here. That is where this result came from. Now we are summing up the log of 1 over the sigmoid transformation for the logistic regression function. So that, again, looked like this. Here was our, at least one form of that sigmoid transform. So this is the ultimate goal here. Okay, we now have our E in. Okay, so let's be very clear about this now. At this point, here is our cost function. That is it. And in logistic regression, we have a specific type of term for this cost function. We refer to this as the cross entropy error. And our goal in maximizing the likelihood of observing the sample is to minimize this cross entropy error. That's what we want to do. We want to minimize really the average sum of these cross entropy error terms here. So that is the cost function for logistic regression. Okay, for linear regression, our cost function was the sum of square residuals, but for logistic regression, our cost function is this bad boy, the cross entropy error term. Okay, so just to kind of compare our, where we're at in terms of logistic regression versus linear regression, right? In linear regression, okay, we did not have a closed form solution. Or sorry, in linear regression, we had a closed form analytical solution, which is what is being described down here. So closed form solution, that was an analytical solution, and the solution to that was the pseudo-inverse transform that we had applied to the y vector to recover the optimal beta parameters. Unfortunately, the cost function for logistic regression here does not have that property. Because the logistic regression lacks an analytical solution, it does not have really a solution where we can write a formula for it. We're going to have to apply an iterative method. Okay, and that iterative method, hopefully you've guessed, is that we're going to use to solve this problem here to minimize that cost function, is the gradient descent algorithm. Okay, and there are many different forms and tweaks of the gradient descent algorithm. This is, again, more of a general idea here that definitely can be improved upon. But the gradient descent algorithm, we talked about this before, and this is a general method for nonlinear optimization. So how do we solve this thing? Well, we started first by initializing an initial guess at iteration 0. And then we thought about updating our initial guess by taking some step, right, where our step gave us our new iteration, our new guess, by taking the old guess and adding some direction to it, moving it in some direction. And in a prior segment, we talked about the direction V that we wanted to think about moving. We wanted to think about moving in the direction opposite to the gradient. So that was the idea here. We had some cost function, some in-sample error function. We wanted to climb to the bottom of it to find this optimal value of beta right here that would solve our cost minimization problem. And the way we're going to do this is by applying gradient descent. So if you watch the segment on gradient descent, this is a real quick rerun there. First step in the process is we go ahead and we initialize those weights. Okay, and then for every iteration, we wind up computing our gradient. And this is the actual form of the gradient. It's pretty ugly here. If you remember your derivative rules of logs and exponentials, you can figure out how that's written. And then we apply our update rule. And the update rule said we are going to take our original guess. Okay, at iteration t, we're taking the original guess. And we're going to add to it the negative, the gradient vector, but we scale it by that learning rate. We scale it by eta, the learning rate, which helps determine our step size. Okay, and we keep iterating to the next step until we hit a stopping rule criteria. And when we hit that stopping rule criteria, then we return the weights, the betas at that particular iteration. So this was the gradient descent algorithm. And one difficulty with the gradient descent algorithm in the current form here is, let's say you have 1 million observations, I suppose, or maybe you got 10 million observations, right? Talking about big data situation here. And if that is the case, Okay, one problem that we're going to run into computationally is that every iteration I have to calculate the sum, which involves me summing over every single observation. So if I have 10 million observations in the training set, at every iteration, and there could be hundreds to thousands of iterations, the computer has to loop through that sum through those 10 million data points. And that can be computationally very intensive. So we're going to talk about a couple alternatives to kind of reduce that computational burden using the gradient descent algorithm. And that is something known as stochastic gradient descent or MiniBatch gradient descent, which doesn't rely on the full set of training data to compute the gradient in every iteration, but rather will compute a noisy version or a somewhat erroneous version of the gradient, which on average is going to move us in the right direction. And what that will allow us to do is to negotiate a trade-off here between the number of iterations and the complexity of the computation for each iteration. It might take more iterations doing this. Okay, if we don't use all of the data points, we're not moving in exactly the right direction, but every iteration will happen much faster. Okay, that is the idea here. So this gradient descent algorithm, the other thing you should notice in this slide is I call it the full batch gradient descent because we are using all n observations to compute the gradient vector. Okay, but there are alternatives. Okay, we could use the full batch at one end of the spectrum, or we can go to the opposite extreme end of the spectrum and use one observation. Okay, sounds kind of similar to when we thought about jackknife estimation, using like one holdout observation. This is not validation, but similar idea here. Okay, we're going to only use one observation to do our estimation technique using this idea of stochastic gradient descent, which we'll talk about momentarily. Now, the batched gradient descent algorithm, okay, for logistic regression, right? What are we doing? Well, we're trying to solve this problem of minimizing that cross entropy error. Okay, and our guide for updating our guess at the iterative process involved moving us along the cost function in the negative direction of the gradient. Okay, dealing with a step size here of delta beta, that's the entire step size, which is determined by scaling the gradient again by this learning rate eta, which is usually a pretty small number, about 10%, 0.1. And at each iteration, we saw that we needed to compute the gradient by using all of the observations in our training set. All of them. And if you have a ton of observations, that can be computationally costly, using the full batch in order to calculate the gradient for this algorithm. So again, the summary of the whole algorithm looked like the following. And this is really the issue for us at this point, that we're looping through potentially too many observations at each iteration in computing this gradient. And we're going to think about improving the computational cost at each iteration by reducing the number of observations that we utilize. Okay, now before we talk about that, I wanted to just jump back and mention one other point regarding the gradient descent. If we were to apply regularization, let's say, to logistic regression, okay, and suppose we took that cross entropy error and we added the penalty term for the ridge estimator. Okay, if you go through the calculus with that penalty term there, lambda, right, over n times beta transpose beta times the sum of the square of betas, okay, then this changes the update rule a little bit. You can go through the math and you can see here you wind up getting this extra term from the penalty showing up, right? The 2 comes out front because it's a beta squared when you take the derivative. Okay, and you can simplify this to what we have in the line below. And when you do this simplification, okay, the term in blue pops out, and the term in blue, you should be able to verify here that this term is definitely smaller than 1. Okay, lambda and n. Lambda was our regularization parameter, and eta was our learning rate. Those are both really small numbers. And then we're dividing them by n, which is a big number, and multiplying by 2. So as long as n is bigger than 2, this is going to be a really small number, and n generally is bigger than 2. So that whole term in blue there is between 0 and 1, meaning there's a slight change to how you can think about implementing gradient descent, at least in terms of the update rule, in that That blue term, what that does is it causes us to shrink our guess at every iteration, right? What was our guess at iteration t? It was this beta term. So we're taking that beta term, beta of t, that's our whole beta vector at iteration t, and we're multiplying it by some constant that is between 0 and 1, that's smaller than 1, okay, which is going to shrink that guess. So now two things are happening at every iteration if we regularize logistic regression. Okay, we're shrinking the parameter guess at that iteration, and we're moving in the opposite direction of the gradient vector at the same time. So again, because we're implementing this type of regularization specifically, it is often referred to as weight decay in the context of gradient descent. When you apply regularization, you're applying what is known as weight decay, because not only at every iteration are you moving in the direction, are you step sizing or stepping in the direction opposite the gradient, but you're also shrinking your original guess. You're rescaling the original guess. All right, so this method, when you apply this type of ridge penalty term to the gradient descent method, whether it's logistic regression, whether it's linear regression or some other nonlinear model that you're trying to solve. You could solve linear regression with the iterative method. You'll get the same solution using the one-step method, or at least it'll approximate that. But if you do this, this is often referred to as weight decay in terms of the effects that regularization has on the update rule in the gradient descent algorithm. Now let's jump back to this problem of having too many observations to loop through when we calculate the gradient at every iteration. What we're going to do here is we're going to do something a little bit different. Okay, rather than using all the observations at every iteration, we're going to randomly sample one. And we're going to compute the gradient on that one observation, which is not the exact gradient. Okay, but the idea being, if at every iteration we do this for a different observation, we will generally be moving in the average direction here. And you can show with some math here that the average direction using the gradient descent with only one randomly chosen observation does move you in the actual direction of the gradient on average. It converges to the right direction. So this is essentially a somewhat randomized version of the gradient descent, which is why we call it stochastic gradient descent. The word stochastic means random. Okay, and the big benefit of stochastic gradient descent is there are fewer observations to loop through, okay, at every iteration. At the extreme, you literally only have one observation to compute the gradient in every iteration. Now the problem is, the trade-off is, you may need more iterations to converge to a solution because you're not moving in exactly the right direction at every iteration on that hyperdimensional cost function. Okay, so the benefits of gradient descent here, of using only one randomly chosen observation to compute the gradient in every iteration, are that it negotiates a cheaper computation for us at each iteration. Okay, the other thing that is also nice is there's some randomization component, which may help us do things like help us avoid situations where we might have maybe multiple optima. Okay, and it's fairly simple to implement. Okay, fairly simple. And we talked about this before, but a general rule of thumb here is we would use a learning rate of about 0.1, and there are other methods that kind of improve on that, that kind of validate the optimal learning rate or help to update the learning rate at iterations. But for our purposes, this will get the job done. And there is kind of a middle ground here, right? Full batch gradient descent, we used every observation at each iteration to compute the gradient. Stochastic gradient descent, we only used one randomly chosen observation, but there is a medium, and that involves here, a case that kind of falls in between those two extremes that we're going to refer to as the MiniBatch gradient descent algorithm. And in the MiniBatch gradient descent algorithm, instead of using only one single randomly sampled observation from the training data, we're going to use M, okay, some smaller subset. Maybe it's 2, maybe it's 5, maybe it's 100, maybe it's 10. Okay, and in some sense, we can think about the optimal M, the optimal batch size, is trying to negotiate a trade-off between computational efficiency improvements versus implementing an accurate final parameter guess. So in practice, I would venture that this is probably a more popular implementation of the gradient descent than those two extreme variations here. But as I mentioned before, this is a very general type of way to solve a nonlinear problem, that is gradient descent. And there are a lot of tweaks and improvements in the AI literature and in computer science and operations research and math theory and applied mathematics that look at improving how this algorithm works here. One of those improvements I mentioned was models involving some sort of a variable learning rate. And again, this is a little beyond the scope of what we're going to get into at this point. But I wanted to wrap up today by talking about another implementation of just a linear regression model, that one-step pseudo-inverse framework here, where we would just use the linear transformation function, so no crazy logistical transformation, just what happens if that thing is just S itself, that is the function. So again, we thought about this framework. We're given some input vector X and our weights beta. We can compute the signal. And linear regression, okay, predicted the expected value of the output given that signal. Okay, but we're going to consider a case here where our output is some scalar. It's either 0 or 1 in the data, meaning we want the actual prediction to be in between 0 and 1 to reflect the weighted probability average in our data, conditional on these features. You might say, well, we did that in a previous segment. We talked about using some threshold for the signal S bar. If it's above that threshold, we say you're high risk of heart disease. If your score is below that threshold, then you're low risk. Why not do that? Well, this is another way where you could think about estimating a probability directly if your Y variable is a bunch of 0 and 1 binary data. And this model that we're going to think about is, why not just regress a bunch of 0 and 1s as the Y variable on your X's using the pseudo-inverse method. And this is referred to in some literatures as the linear probability model. And the reason why we don't do this, I think, is maybe clear graphically here. With logistic regression, we have this nice sigmoid function. And what that does is it guarantees the output has a probability interpretation. It never goes below 0 and it never goes above 1. It reaches 0 and 1 asymptotically as the signal itself gets either arbitrarily large, right, in the right direction, or arbitrarily small, it approaches 0 in the left direction. So the logistic regression model was nice in that the output was always bounded between 0 and 1. Now, if we use a linear probability model, okay, which I've illustrated here diagrammatically, right? Here's our linear probability model. Okay, we had some data up in this diagram. Okay, I didn't show those data points, but you can imagine there's all these different data points up here, right, that we're trying to fit through. Okay, and if we used a linear probability model, you might almost notice right away that we have a problem. In that, if we get extreme values for certain observations, like let's suppose we have an X value that is over here. Suppose the X value is over here at that little orange threshold that I just drew. Well, under logistic regression, that X value, okay, would still have a positive fitted value that can be interpreted as a probability. But you'll notice under the linear probability model, the fitted value, if we go down to the regression function, and then we go over, winds up being negative, and you do not get a probability interpretable fitted value here. So the problem with doing classification this way, if you were thinking about why not do it this way, this is why, and I had a few folks ask me, which is why I'm cycling back and kind of touching on this topic. What this means is, for very extreme cases, for situations where our input data is far from the mean values of those inputs, okay, some of the fitted values or some of the predicted values might be bigger than 1 or might be smaller than 0, right? If X is too large, then the fitted values along that red line could be bigger than 1, meaning we lose this problem, or rather we lose the probability interpretation, if you will, of the output here. Now, this problem is not as bad if we wind up only plugging in data that is very close to the center of the distribution, where the fitted values would fall along the red line and would not be outside of the 0 to 1 interval. And that happens along the red line only in this range that I'm going to highlight in purple. Okay, so as long as we plug in an X value somewhere near the mean of the X values, then we will be on that probability line there in red, but only between 0 and 1. We won't go into negative predicted value territory or predicted value territory that has a probability greater than 1, which is impossible. Okay, so just to conclude here, side by side look at our models. Right, given some input vector and some weights, some parameters, we looked at really applying linear regression to classification. Okay, we discussed just linear regression in general, and now we have an idea of what logistic regression is. So in all three cases here, right, we have some key differences in terms of the features of our hypothesis sets. Right, in the case of linear regression for classification, we had a hard threshold. We had a very rigid function. It was either positive or negative, 1 or 0. Okay, if the signal was above the threshold S bar or below. Under linear regression, we didn't have any threshold. It was a linear output that could go between, negative infinity to positive infinity in theory. And logistic regression, we had a soft threshold function, right? It smoothed that signal out in between some number between 0 and 1, which numerically we can interpret as a probability measure. So that wraps up our discussion here of logistic regression and some of these variants of gradient descent that can be applied to solve it. We'll see you soon for an example of implementing logistic regression.